Okay, let's get started. So last time we introduced cyclic groups and we proved a couple of first properties about them. So this was one of the statements that we proved, and this is going to come up a couple of times today. And a lot of the arguments sort of revolved around using the division algorithm, and that is going to continue today. So let's just quickly see an example to show how you might use this theorem from last time. So let's suppose we have some group element A with order equal to 30. Then we might ask what is the group generated by A to the 23. And from this theorem we know that the GCD of 30 and 23 is equal to 1. So this this a priori just kind of random looking group, we actually know that this is equal to the group generated by A to the 1, which is equal to the group generated by A. So basically what this shows is that it allows us to replace complicated or unwieldy generators with simpler ones. Okay, so this is one way that this theorem might be used, just to kind of rewrite a subgroup that might be handed to you into a simpler form. Okay, so the main goal of today is to prove something called the fundamental theorem of cyclic groups. And this theorem will tell you basically everything you might want to know about the subgroup structure of cyclic groups. So let's go ahead and see the statement of the theorem. So it has three parts. The first part says that every subgroup of a cyclic group is also cyclic. And then, so that's going to be sort of the meat of the proof, and then the other two parts will sort of fall out of that. So the second part says that if the order of some group element A is equal to n, then the order of any subgroup of the group generated by A is a divisor of n. Okay, so this is maybe not that surprising based on the examples that we've seen, that the order of subgroups will divide the order of a group. So that is going to hold true in a more general setting, but we'll prove it later. But for now, we'll just get the statement for cyclic groups. And then the third part is that, so it says, it sort of strengthens upon part two. So it says that for every positive divisor, let's call it K, of n, the group generated by A has exactly one subgroup of order K. K, and it is this subgroup of order K. So it's going to be the group generated by A to the n divided by K. Okay, so this part 3 is really powerful because basically it says if I hand you any cyclic group, once you know its order, then you know what all of the subgroups are. I guess once you know its order and a generator, you know what all of the subgroups are. Okay, so first let's do a quick example just to illustrate this. So let's look at Z mod 6 with addition. So a few days ago we computed sort of by hand all of the subgroups. But now using this theorem, basically what we have to do is first list the divisors of the order of the group, which is 6. So those would be 1, 2, 3, and 6. And then now we know that there's going to be a unique subgroup of that order. So, and that's going to be generated by the following elements. So we get these generators. So we know that this, the whole group Z6 is generated by the element 1. So what we do to find the generator of each subgroup, well, we're going to, I guess in this case we're looking at an additive group, so we're going to multiply by 6 divided by the divisor. So we'll get 6 divided by 1 times 1, so this will be 6. Which I guess in this case is equal to 0, so I'll just write this as 0. We would have 6 divided by 2 times 1 is equal to 3, so 3 is the generator of the unique group of order, subgroup of order 2. 6 divided by 3 times 1 gives us that 2 is the generator, or a generator of the subgroup of order 3, and then finally we know that 1 generates the whole group. So what is the subgroup that we get out of each of these? So this first one would just be the one containing the identity. This one would be the identity and the element 3. This one contains the identity, 3, and, it's generated by 2. The identity, 2, and 4. And then lastly, we get the entire group. I'll just write Z6. Okay, so this is just an example of how you might use this theorem to analyze the subgroup structure of a cyclic group. Okay, are there any questions up to this point or about the theorem statement or about this example or anything like that before we launch into proving the theorem? Yeah.
Just a quick question. Why is 6 divided by 1 times 1 0? Is that just because it's like the
Yeah, okay, so we're going mod 6. So this would be 6, but 6 isn't an element of this group, right? Because this is just the numbers 0 up to 5. So this is 0 mod 6. Yeah. Yeah, okay, so the way the theorem is phrased, it is in terms of like, I've picked a specific element and then I'm generating a cyclic group out of that element, right? But in this, like, so that means that if you wanted to analyze like a specific cyclic group, you just need to identify a generator. So like, yeah, so in this case, we've written the whole group Z6 as a cyclic group generated by the element 1. Other questions? Yeah.
Why is it under the generators column? Why isn't it times 1 after every single division?
But yeah, so I picked like 1 as my special generator of the whole group. So this is acting as like the A in the theorem. Yeah, and I guess since it's an additive group and not a multiplicative group, like. this means like add 1 to itself that many times. Yeah. Yeah.
So since it's an additive group, when you're generating the filter, is it like for divisor 6, 3, is it like 2 plus 2 plus 2?
Yeah.
So not like n or 8 then?
Yeah, exactly. So, okay, in this group, we're working, so it's additive. So like if I were to re-express this, I would say I'm really looking at n divided by k times an element A. And then when I generate the group, instead of looking at products and looking at just adding this to itself multiple times. Oops, I don't really want these brackets. I want this to just be a set. Okay, other questions? Okay, so let's prove part 1 of the theorem. So we're going to prove that every subgroup of a cyclic group is cyclic. Okay, so I'm actually just going to copy this. Okay, so the way that I'm going to do this is I'm going to just take an arbitrary subgroup of my group. So we're going to let G be a cyclic group and let H be a subgroup of G. Okay, so then we need to show that H is cyclic. So to start off, I'm just going to eliminate the case that H is the trivial group. So if H is just the group containing the identity, then it's already cyclic. So if we're in the other case, so otherwise, H contains some other element. Okay, so let's assume, so since G was a cyclic group, let's say, so since G is cyclic, we have that G is equal to the group generated by A for some A in G. Okay, so that means that this element that we know, so H contains some non-identity element, and that element is of the form a to the t for some t. So let's call this other element B for the moment. So we have that B is equal to a to the t for some t, since B is in the group G, which is generated by A. Okay, and moreover, we can assume that T is positive, so Y, I'll make a brief argument for this. So we can assume T is positive. So we know it's not equal to 0 because that would mean that B was the identity and we picked it specifically to be a non-identity element. And if it's negative, since H is a subgroup, we have the inverse of that element. So If t is less than 0, then a to the minus t is also in H, and minus t would be greater than 0. So because of this, we'll just assume that this exponent t is positive. Okay, is everyone on board up to this point? Okay, so I'm going to let m be the least positive integer such that a to the m is in H. Okay, so we know that m exists because, like, it could be t, this number that we've already shown that we have, but let's let m be the smallest possible one. Okay, so then what we will do is show, so I'll make a claim. I'm going to claim that my subgroup H is actually equal to the group generated by a to the m, and this will show that H is cyclic. Okay, so once we've proven this claim, we're done. And I will just do this by showing both inclusions. So first, we know that the subgroup generated by a to the m is a subgroup of H because a to the m is in H and H is closed under the group operations. So that automatically means that anything that appears in this subgroup generated by a to the m, that will also be in H. Are there questions up to this point? Okay, so let's prove the other inclusion. So we'll show that H is contained in a to the m. So for this, let's assume we have some element, I guess I already used the letter B, so let's assume we have some C that's in H. Then since C is also an element of the group G, we have that C is equal to a to the k for some k. And now is the moment when we will apply the division algorithm again. So we can write k as m times q plus r. So recall m is this exponent on, so this number m comes from the a to the m. Okay, so I'm rewriting k in terms of m using the division algorithm, and r is some number, possibly 0, but less than m. Okay, so then a to the k is equal to a to the mq times a to the r. And so we can rewrite a to the r as a to the minus mq times a to the k. And from this, we see that a to the r is in fact contained in H, because we already knew that a to the k was in H, and then we also know that any multiple of a to the m is in H. Okay, so that gives me that a to the r is in H. But m was the least positive integer with a to the m in R, so that forces R to be 0. So since m is the least positive integer with a to the m in H, we have that R must be equal to 0. So that means that so our element C, so let's write this. So our element C is just equal to a to the mq, which is an element of the subgroup generated by a to the m. And that concludes this part of the proof. So then we know that H is a subset of the subgroup generated by a to the m. And that means that, in fact, H is equal to the subgroup generated by a to the m, and so H is cyclic. So that completes the proof. Are there questions about this? So this is like a similar application of the division algorithm that we saw in the last lecture. Okay, so that gives us the first part of the theorem statement. So we still have 2 other parts to prove. So let's bring those down. Yeah.
I was wondering, I was trying to remember, what did we end up using t for? Because we said b equals a to the t for some t greater than 0, but then did we end up using that factor?
No, okay, so yeah, so this, why did we go through this argument of finding an a to the t inside of H? Bean. So we wanted to, I guess the goal of like that entire part was we need to let m be the least positive integer such that a to the m is in H. So in order to like have that m exist at all, we have to show that there is something in H, something of the form a to the t. So this was basically just like set up for ensuring that we do have a to the something inside of
Like
H.
that was t. Like if m isn't anything else, it's at least going to be t.
Yeah,
Okay.
yeah. Other questions?
What was the point of like talking about like G at the start of it? Talking about like B at the start of it?
Yeah, okay, so this, so basically like this, I'm just gonna like bracket this off. So this entire part, the goal was just to show that there is a positive integer t with a to the t in H. So that was like what was accomplished in this part of the proof. We just showed that there's some positive integer t with a to the t in H. I didn't write this in the clearest possible way.
Oh, so that lets you claim that m is a positive integer in H.
Yeah. Yeah. So that like enables us to do this step. Yeah. Which I guess in a way is like an application of the well ordering principle. But okay, so that was the first part of the proof. So here are the other two parts that we still have to prove. So I'm going to give you all a few minutes to think about how to prove part 2. And my hint is to use the fact that we have already proven in the previous part that if you have a subgroup, so let's say H is the subgroup, that H is equal to A to the M for some M. So this is like work that we did in the previous part. But I'll give you a few minutes to think about how we might prove 2, and then we can talk about it. Okay, so did anyone figure out how to do this part of the proof? Yeah.
Isn't it just using the division rule that the order of a to the k is n divided the order of a divided by GCD of and the order?
Yeah, so we had this theorem from last time that tells us how to compute the order of this subgroup generated by A to the M. So this is going to be n divided by the GCD of n and m. And whatever this number is, this is a divisor of n. So this is a divisor of n. And since that number is equal to the order of h, that means that the order of h divides n. Is that clear? So we're just using, this is, like this equality is by a result from last time. This equality. Other questions about this part? Okay, so let's prove the last part of this theorem. So for this, so we're trying to show that every positive divisor k of n, this group has exactly one subgroup of order k, and it's given by this thing. So let's let k be any positive divisor of n. Then first, let's just exhibit a subgroup that has order k. So let's show that there exists, so there is a subgroup of this group generated by A of order k, and then we'll show that it's the unique one. Okay, so let's look at, so the theorem says that it's going to be this subgroup, so let's look at this, a to the n divided by k. So the order of this is equal to, by the previous theorem, this is n divided by the GCD of n and n over k. Okay, and then since, so n over k is a number that divides n, so the greatest common divisor of n and whatever this thing is just going to be this thing. So this gives me n divided by n over k, which is then just k. Okay, so that means that so we'll just write the conclusion. So the subgroup generated by a to the n over k is a subgroup of the group generated by a of order k. Okay, so now let's prove that this is the only subgroup of order k. Are we good up to this point? Okay, so let's suppose H is a subgroup of the group generated by A of order k. And we'll prove that it has to be equal to this one that we've already written down. So in the part one of the proof, we showed that H is equal to A to the M, and we also showed in part two that M is a divisor of N. Okay, so then I know that K is equal to the order of A to the M, because we're assuming that this group H has order K. And by the theorem from last time, this is then equal to n, this order is equal to n divided by the GCD of n and m. Since m is a divisor of n, that means that the GCD of n and m is m. And then just rearranging this equation, we get that m is equal to n divided by k. So what does that mean? H was defined as a to the m, or we showed that it is equal to a to the m for some m, and m is equal to n over k. So we actually have that this arbitrary subgroup of the group generated by A of order k, in fact, has to be equal to the one that we already knew about. So that means that this one is the unique subgroup of order k. Okay, and then that finishes the proof. Yeah.
I think I understand that m can be expressed as n over k, but I'm a little confused about why this is
Why it's unique. Okay, so we picked like an arbitrary, H is just any subgroup of this thing, and it has order k, and then we showed that it was equal to our favorite subgroup of order k. Yeah, so that means that that is really the only one. Yeah.
Do you remind me where we showed that A is generated by A to M for M is the divisor of N?
Yes, okay, so do you agree that H is generated by a to the m?
Yeah, I just forgot where exactly we showed that.
Yeah, so that was in
part one.
part one, yeah. So like, yeah, let's see. So this part is like part one, and then the fact that m divides n is part two.
Okay.
Yeah. Other questions? Yeah.
Yeah, so in the first part, how do you know that a to the n over k is a subgroup?
How do we know that a to the n over k is what?
Is a subgroup.
So we know, okay, so k is a divisor of n, right? So this is just a number. So then a to some number, that's going to be an element of the group generated by A. And then we showed that that like taking a group generated by some element is a subgroup always. Yeah. Other questions? Okay, so I'm gonna just write down basically what this theorem says. We're just gonna translate the theorem into our favorite cyclic group, which is z to the n, or sorry, z sub n. So this is like just rewriting the fundamental theorem of cyclic groups for z mod n. So what this says is that for each positive divisor k of n, the set given by, so it's going to be generated by n divided by k, is the unique subgroup of z mod n of order k. And furthermore, these are all of the subgroups. So earlier in the lecture, we looked at the example of Z mod 6, and this is just like a translation of the theorem statement to this special case of Z mod n. So if you're handed any Z mod n, then like automatically you can determine all the subgroups. You know they're all cyclic, and you know what the generators are, and you know how many of each order there are and what their possible orders are. So I want to give you another statement about cyclic groups, but I don't think we'll get all the way through the proof in the time we have left. So I'm just going to give a definition leading into that. So this is going to give us a function, and that function will allow us to count the number of elements of a particular order in a group. So this is something called the Euler-Phi function. And it's written like, okay. So I'm going to let phi of 1 be equal to 1. And then for any integer n greater than 1, I'll let phi of n denote the number of positive integers less than n and relatively prime to n. Okay, so this phi of n is something called the Euler-Phi function. What does it mean? So I'll just note a couple of like properties of this function. So note just by the way we defined these U groups, the order of UN is equal to phi of n. And I guess you can easily say what phi of any prime number is. So what is, I wrote the wrong kind of phi. What is phi of a prime? So it's the number that are less than and relatively prime. Yeah. Yeah, so this is going to be p minus 1, because everybody less than p is going to be relatively prime to p. And this function has a lot of other interesting properties, and it appears in like a lot of different contexts. So maybe we will have time to prove this. We'll see. Okay, so here's how it's going to appear for us. So we have the following theorem. So if D is a positive divisor of n, then the number of elements of order D in a cyclic group of order n is equal to phi of D. Okay, so phi counts the number of elements of a certain order in cyclic groups, which is pretty cool. So let's see how this is proved just in a few minutes. So by the theorem, we have one subgroup of order D. Okay, let's set this up. So let's start off with, let's let G be cyclic and have order n. So we know that there's one subgroup of order D, and we'll call it the group generated by A. Because we also know that this group is cyclic, so it's generated by some group element. And then if we had that B is another element of order D, then the group generated by B is also a subgroup of order D, but since we only have one subgroup of order D, that means that it actually has to equal the subgroup generated by A. So this is like so this one has order D, but there's a unique one. So that means that B is equal to A to the K for some K. And then we know by this theorem that we had last time that the order of A to the K is equal to D divided by the GCD of D and K. But this is again supposed to equal D, so that implies that this GCD of D and K has to be equal to 1. So the number of possible elements of order D, this equals the number of K's with the group generated by A to the K equal to the group generated by A, but we know that this is equal to the number of K's with GCD of D and K equal to 1. So this is counted by phi of D. And that completes the proof. So I know that was kind of rushed at the end. So if you have questions about this, you can hang after to ask them. And next time we will be talking about permutation groups. Yeah. Yeah. Yeah.
Is there a way to know phi for any number, or do you just have to count?
There is. And there's a lot of interesting things you can prove about phi, and they're pretty fun problems. So I might assign them on the problem set, even though it's kind of a side quest. Like, it's not really going to, like, reappear, but they're, like, fun problems. So I might, like, put the, yeah. I have office hours right now. It's in my office. Yeah, this.
Right before that. Yeah,
That
for
one.
Zn. Why? I didn't quite follow the last statement for the are. Okay, these are all the subgroups. Why is that the case following from the original theorem?
Okay, yeah. So you know, every subgroup of a cyclic group is cyclic, and we also got that its order has to be a divisor of n.
Yeah.
But we also know that for any divisor of n, there's exactly one.
Wait. So yeah, I get that the order of the subgroup divides n, and so for every n positive.
Okay, yeah. So let's go back
that
to.
just show you.
Okay. So let's say I give you Zn and you list out. So you know that for every k, I get one subgroup of order k for
Yeah.
every divisor of n k.
Exactly one.
Exactly one. But then, suppose you had a subgroup that wasn't one of those. Well, it has to have order that divides n. So actually, it is one of the ones in your list.
Oh, okay. So that'd be basic proof by contradiction, right?
Yeah.
Okay. Cool. Thank you.
Was it further?
Yeah. How is it that you know that the order of a to the k is d?
How do we know that the order of a to the k is what?
Is d equal to d? Like I understand this middle equality here, but like
Oh, cause we suppose
we're
that B
assuming
was
B
a
is-
D. Yeah, B
oh, and
was
B
of
is A
order
to the
D,
K.
and B is A to the K. Yeah.
oh okay, got it. Thank you.